So here's my outline. The first question is why UV completion? I have to try to explain how UV degrees of freedom can affect our description of macroscopically large black holes. And then what UV completion? Here I'm going to reconsider Stella's quadratic gravity quantum field theory. I think we can all agree that it's at least a very tantalizing theory, and I still think it's worth thinking about the interpretation. So I want to show some examples of calculations, some of which are done by others, and what they can teach us about how to view this theory. So with this UV completion, then I can get back to this not quite black hole, which comes out of this quadratic gravity theory, at least the classical version of it, and describe some of the main features of 2-2 holes. So the question of why UV completion, I think it's good to look at an example from QCD, and that's quark matter. So quark matter occurs when a high enough density of quarks inside some region creates a hole in the chiral condensate. And that can be described by a Lagrangian like this. It's a type of linear sigma model. And if this potential is chosen correctly, then this model models some mesons of QCD, the lightest scalar and pseudoscalar non-nets. At the minimum of this potential, the value that phi ij takes represents the chiral condensate. So it's because of the last term in L, a large enough quark density can push phi UU and phi DD close to 0, and that's what forms a hole. So the radius of such a hole can be arbitrarily large compared to the fundamental scale in the theory. So even though we're talking about macroscopically large objects, I'm saying that we can't understand such a thing from within the low energy theory, which in this case is the chiral Lagrangian, where phi dagger phi equals 1. So I'm saying we need some understanding of the UV completion in this case, and that's what this Lagrangian is doing for us. So what about a hole in space-time? What in the world does that mean? Well, let's take it to mean a hole in the volume of space-time. So consider root g over r squared is the square root of the product of these metric functions that are occurring in the spherically symmetric metric. So a hole is a region then inside some radius where this quantity is getting small or going to 0. So what does GR say about such holes? Well, not much. GR is the analog of the chiral Lagrangian. And for a black hole, we know that the product of these metric functions is 1. And I think that's the analog of phi dagger phi equals 1. When we add matter and look at a star, B of r can get small, but A of r, as far as I know, is greater than or equal to 1. And I know that at 0 radius, it has to equal 1. Now I'm going to be saying that for a UV complete theory, something much more dramatic can happen for a sufficiently large matter density. And that is a hole in space-time. I'm talking about a 2-2 hole that emerges from quadratic gravity. So these are solutions that have to be obtained numerically, and I'm showing on the top plot a plot of these metric functions where A is in blue, and this object has a radius of 80 Planck units. So outside that radius, it goes over to the short-shelled metric, and inside, these metric functions get small very quickly. The vertical axis is a log scale. So yeah, these metric functions are collapsing on the inside. When you get close to the origin, they're going like r squared. And so at r equals 0, the whole metric vanishes at that one point. So the bottom plot shows this quantity I was talking about, root g over r squared. It's constant on the outside, and it drops off a cliff as you go inside. So that's on a linear scale, and the log scale version is shown by the insert. So yes, A of r is getting small, and that means a collapsing spatial volume. and it means a much larger matter density and pressure for the same amount of matter. So we're starting to see why matter can resist its own collapse into the time-like singularity that does exist in this 2-2-hole space-time at r equals 0. So that's all I want to say about 2-2-holes at the moment. I want to make a transition to the next part of the talk, to the UV completion. And I just want to say I agree completely with how John describes this UV completion. But I'm going to just take a somewhat different view here just to see where it leads. So this is the local quantum field theory for gravity that Stella spelled out in 1977. And we all know that it's renormalizable and the energy is bounded from below. But, and it's a big but, it requires negative norm states or ghosts. Well, I'm going to approach this theory similar to perturbative QCD. So that's a perturbative theory of quarks and gluons, but those fields are not the actual asymptotic states of the full theory. So you could take this perturbative theory and calculate scattering of on-shell quarks and gluons if you wanted to, but those are not physical processes. In fact, you have to work quite a bit harder in this theory to make contact with physical processes. And that's a whole industry in QCD to do that. So I'm going to say that perturbative gravity quantum field theory is maybe somewhat similar and hopefully not so difficult, because these negative norm states are not the actual asymptotic states of the full theory. And so we again have to watch out for unphysical processes. And the slightly new thing here is that some of these unphysical processes can come with negative probabilities. So we have to talk about negative probabilities, but just remember, it's in the context of unphysical processes. So a differential cross-section or a decay rate is up to some simple factor, like a flux factor in the case of a cross-section. It's nothing more than a differential probability. So I can write this dp as a phase space factor for the final state times a matrix element squared divided by these norm factors. And the only thing new here is this eta j in the norm factor, where j labels the particle. So eta j is plus or minus 1 and minus 1 for a ghost. So when the total number of ghosts in the initial and final states is odd, then the probability is negative. Now, Feynman argued that negative probabilities occurring in intermediate stages of a calculation are okay, as long as they cannot be physically realized. And I think that's what's going on here. These negative norm states correspond to states that are not only massive and unstable, but they have a negative decay rate from the formula I just gave. And when you figure out what that means, it means that these things decay backward in time. And they propagate positive energy backward in time before decaying into normal particles that appear in the final state. So yeah, this was all nicely described by John on Monday. So I'm saying that there's no sense in which these things can correspond to asymptotic states. So it's not like a slightly unstable normal particle, which in some approximation could be considered an asymptotic state. So I say we can't do anything like that here. And so the production process of a ghost must be combined with its decay process. And the product of these two negative probabilities is positive. So I'm just saying this is an example of how unphysical amplitudes can build up into something that's physical. So this stellar perturbation theory is standard, except for this massive spin 2 ghost Baire propagator. And the latter only differs from the Feynman propagator by an overall sign. So loop diagrams have standard causal structure. By that, I just mean the I epsilons are all in the right places. Now you can consider the dress propagator, and this is very useful because it does offer a glimpse into the full theory. So as John has explained, it has the wrong overall sign. The pole location is now also wrong. And it's from this structure that gives us this acausal backward in time decay. So yes, it's very useful to consider to see that. It's also useful when the pole structure of the ghost is important, in analogy with how the Z pole is treated, for example, in some E plus E minus into Z type process, and you're sitting close to the Z pole. But otherwise, we should see what we can learn from this naive stellar perturbation theory. So the first example is graviton scattering, which we heard about yesterday. It was calculated by these authors in quadratic gravity. They considered external massless gravitons only, so they had no worries about negative probabilities. And they found that the result was identical to the GR amplitude, which, as we also saw yesterday, is somewhat surprising. And these authors, well, first of all, yeah, this seems to be true for any tree level amplitude involving only massless gravitons and possibly normal matter. So in this case of this kind of amplitude, these ghosts were, in the theory, are canceled. So, okay, anyway, these amplitudes are the same in the two theories, but the meaning of these amplitudes is different because quadratic gravity is a UV complete theory. So it should be describing these amplitudes in the high energy limit as well. And of course, quadratic gravity also describes other states. So we should also expect the theory to describe the scattering into those massive states as well. So I want to get back to that, but in the meantime, let me just say that this theory has unitarity, but not positivity. In other words, unitarity can live with negative probabilities. So SS dagger equal 1 is still an identity. We just need the proper representation of the unit operator. And that means we have to keep these norm factors in the definition, which bring in these odd minus signs. So we can go using standard definitions to bring in this M matrix element, and then we get the optical theorem. So that's on the right-hand side is the sum over these intermediate states X, and these norm factors for these states X appear. I've also divided both sides by the norm factor for the initial state, and that means that each term on the right-hand side is a probability. So we have positive and negative probabilities on the right-hand side, and thus no positivity. So let's go back to this graviton scattering amplitude. It happens to go like E squared. So that raises a question. Does perturbation theory break down at some high E? Because you might expect that, because the imaginary part of the amplitude by the standard optical theorem goes like the tree level amplitude squared, and that looks like it's going to get larger than the tree level amplitude itself. Well, here's some other authors who have looked at this question, maybe not exactly using those words, but they first of all considered a higher derivative scalar gravity having negative norms, and their results say that the answer is no. Perturbation theory does not break down. And then they went on to quadratic gravity and considered graviton scalar scattering. So these are the diagrams. The final state wiggly line could be a massless graviton, a massive ghost, or a massive gravascalar. So they considered all those. And they found that the leading naive e to the fourth behavior that we would have expected in the imaginary part of the amplitude cancels, and perturbation theory survives. So we're saying that the survival of perturbation theory requires this lack of positivity. Those authors never directly, or they were quite careful never to mention words of negative probability or negative cross sections. So I am putting a little bit of my interpretation onto their nice results. So let's get back to graviton scattering again. So yeah, we want to consider a general final state, including on-shell ghosts and or gravascalars. So this is what I've done, and I've looked at these amplitudes. They again all go like e squared. So yeah, then the question is there some kind of similar cancellation? Well, what I find is that the final states, other than for the three final states that I list there, all the other amplitudes vanish. And they vanish because of cancellations between diagrams and only when everything is on shell. So yeah, in particular, amplitudes with a single ghost vanish. And there's another example of that vanishing of single ghost amplitudes. That's the decay of a single on-shell ghost to two gravitons. So anyway, in the graviton scattering, the final states that don't have vanishing amplitudes all have positive probabilities. So well, that sounds nice initially, but as we've seen, then there are no cancellations in the optical theorem, and then it seems like perturbation theory would break down. So what's going on then? Well, let's explore a bit what happens when the Einstein term is removed. Then you've removed the mass from the theory, so there are no massive states. So what I did was just very naively repeat the calculation, but just remove all the Einstein pieces in the propagators and the vertices. And in that case, the amplitudes again, well, again, surprisingly, has a surprising result, which is that these amplitudes vanish. Again, because of non-trivial cancellation between diagrams. And it's not clear why, because you can't use some conformal argument. The R-squared term is in the theory. So anyway, if the Einstein term then vanished in the UV limit, then we might think, because of this result, that so do the amplitudes. So if this is true, then the problem we're running into appears to be connected with the constant coefficient of the Einstein term. So that leads to what I think is a more attractive and QCD-like picture of quadratic gravity. And that's for the fundamental theory to contain no Einstein term and have the effective Einstein term being generated when the running coupling of the theory grows strong. So in this picture, the Einstein term fades in the UV. And so it could be in this case that the pure gravity sector approaches this apparently vanishing amplitude limit that I'm talking about. And so in this case, it could be that pure gravity amplitudes could remain bounded. So that's the pure gravity sector. The other example I gave was scalar graviton scattering. It seems to go some other way, and it doesn't need bounded amplitudes for perturbation theory to survive. Okay, so basically we're finding from what I've seen so far that there is no bare Planck mass allowed in this theory. And perhaps it's also true that no bare masses of any kind are allowed in this gravity quantum field theory. Okay, so that's all I want to say about the quantum UV completion. Let's try to get back to the classical theory. Now, the naive classical theory may not have much meaning since the ghost is not an asymptotic state of the quantum field theory. So nevertheless, I'm going to go ahead anyway, and hopefully the static solutions can tell us something. So I can go over a little history of tutu holes, and this doesn't take long because even though this topic has been kicking around for a long, long time, there hasn't been much activity. So Stella made the same transition from QFT to the classical version in 1978, and he, as he described earlier, found these three classes of solutions. So much later, I was looking at quadratic gravity, and I found these tutu solutions have 5 parameters. That actually agrees with the 6 parameters that Kelly just mentioned, because I I did not count the trivial parameter, which is the overall scale of the B function. So, which also, by the way, this number of parameters, as you saw in this table, makes these solutions the most generic of these three classes of solutions because it has the most parameters. Anyway, as he also mentioned that I found that solution in this case. So much later still, then they gave a nice discussion of the black hole-like solutions and the 2-2 solutions with possible matter sources and parameter counting. Then with Jing Ren, we found solutions, and here we started to call these things 2-2 holes, having a matter shell as a source. But even though, again, all this was numerical, we were able to find the scaling behavior of the interior solution for any m. And by the way, m can be arbitrarily large. So we have a pretty good idea what these large 2-2 holes are like, even though we can only actually produce numerical solutions for small m. And then a little later, I found these solutions with a relativistic gas as the source. And so these are the things that I would call realistic 2-2 hole solutions. And then there are a couple of other topics that I can't go into here. So let's talk about these 2-2 holes that have a thermal gas as the source. So I've already told you about how these metric functions, how they behave close to the origin. I've also mentioned that we know the interior scaling, so that means we know how these coefficients, A2 and B2, depend on m. And they go like 1 over m to the 4th. So yeah, these metric functions get extremely small. The relativistic gas is standard, and it has a temperature which is R dependent, going like the inverse square root of the B function times T infinity. So the field equations are, as Kelly was mentioning, they're cumbersome to deal with. And I guess they form kind of a moat around this whole subject. But anyway, they do finally determine the metric functions, and in this case, a particular combination of parameters. So M2 is the ghost mass, and N counts the particle degrees of freedom of nature. There's a couple of exact results. The total energy is 3 over 8 times M, and the entropy times the T infinity is the same as for the same mass black hole. So yeah, where does this entropy come from? Well, there's no mystery here. It just comes from the entropy of a hot gas. So you just do some integral over something involving temperature cubed. And you remember that temperature has a 1 over root b in it. So if you keep track of the factors of m or radius that I've been talking about, you can see that this integral goes like, in the end, r squared as an area. And the result is the same as for a black hole, up to this constant zeta. And so again, yeah, this area law result is due to that interior scaling of these metric functions. And zeta is given by that expression. So I expect the ghost mass to be of order the Planck mass, and n in the standard model is well over 100. So this zeta can be easily larger than 1. So the entropy of this thing is greater than the same size black hole. And the T infinity is smaller than the Hawking temperature. So just from a simple entropy argument, 2-2 holes can be preferred over black holes as the endpoint of gravitational collapse. Here are plots of two densities. By density, I just mean the integrand of the R integral that gives rise to the quantity. So for the entropy density, it's spread over the interior in this way. And then there's also the action density. If you write the action in terms of C and R squared, in the interior, it's the Weil squared term that dominates. And when you plot that, it's also spread out throughout the interior, to be compared with the Schwarzschild case where this quantity is blowing up. So because of this, you could call a tutu hole nothing but a ball of Weyl action. Now, I've mentioned the singularity in the solution, so what effect does that have? The most important question, I think, for that is the wave equation. And if we consider the wave equation in spherical coordinates, then it turns out that around a tutu hole background, the wave equation is less singular than in flat space. So the scalar wave equation, for example, has the usual angular momentum term, which makes a singular contribution, but not here because B of r is going like r squared, close to r equals 0. So this just means that all the L waves behave like L equals 0 waves. So they all penetrate down to the center, just like S waves do. So all this is important for the study of gravitational waves. And in that case, it's standard to change from the r coordinate to the tortoise coordinate. And the wave equation takes a form like this that depends on just a potential. So we can plot that. So for any very compact object, you see this angular momentum barrier peak, which sits at r equals 3 gm, the light ring radius. And then well inside that, we can compare different objects. For a black hole, you actually have to go off to minus infinity in this x coordinate to reach the horizon. So I'm really just plotting a truncated black hole. A gravistar or any other star has this angular momentum divergence at the origin, whereas the tutu hole, as I said, is finite at the origin. There's just some minor structure there related to what's going on inside the tutu hole. But as you can see, a good approximation to a tutu hole as far as the gravitational wave is concerned is that it looks like a truncated black hole. And that gives rise to this whole story of echoes. As you can now imagine, because of this one-dimensional cavity structure with one end that's slightly leaked. So every time a wave hits that barrier, some of it can get through. And so if you had one pulse that bounces back and forth on the inside, that can give rise to echoes emerging on the outside. So that's a nice idea. But this way to talk about it requires a very simple initial condition to have this one pulse that bounces back and forth like that. A more general feature of this setup, that is the 1D cavity structure, is a very closely spaced resonance pattern. And I say closely spaced because this cavity is effectively stretched. So delta x, the size of the cavity, is enhanced by a log of something like the radius over the Planck length. So that can be almost as large as a factor of 100. And that means that delta f, the spacing between the resonances, is 1 over the round trip travel time, which is just 2 delta x in tortoise coordinates. So I've pictured here the resonance pattern in a particular case of a very random initial condition. So not this case of one thing bouncing back and forth. So the very random condition here is showing up by random heights in these resonances. If you were to look in this case of what's going on in the time domain, you would see no simple echoes at all. And if you added a little LIGO noise to it, you wouldn't see anything. But so far, that's the way LIGO has chosen to look for echoes, in the naive way where they look at the simplest possible type of echoes in the time domain. Whereas I think it would be better to go over to the frequency domain and take the absolute value, like we do in particle physics, where we're always taking the mod squared of some amplitude to look for resonances. Well, that's yet to be done at LIGO. And for that reason, I've been spending a lot of my time trying to figure out how to analyze the LIGO data and possibly look or see these type of things. That's a whole different story. So I think my time should be near the end, so I'll just conclude here. So I think I've been trying to argue that UV completion can change our view of black holes, and the new view of black holes can lead to signatures that can be searched for in data that has already been collected. And then I also described Stella's local gravity quantum field theory that supports perturbative calculations. It's just that you have to think about what the meaning of these results are that you would get. Like, is it a physical or is it an unphysical process? Although we've already seen that calculating unphysical processes can be useful to see how the perturbation theory is working. And then, is it sensitive to the difference between the full and the bare ghost propagator in some other way? And is it sensitive to a possibly strong coupling occurring close to the Planck scale? Okay, so I think that's a good place to stop. Thank you.
Thank you very much for your talk. Thanks a lot. Very nice talk. And we have time for at least a couple of questions. First, I think Richard Woodard, I guess.
Hey, Bob, thanks for giving us this talk, explaining your point of view. I'd like you to respond to an issue that I've emailed you privately, you and John privately, and that is that it seems to me like the classical theory, the classical higher derivative theory that you're talking about can't possibly represent the classical limit of the ultraviolet complete theory that you and John claim to have. The reason why is because the spectrum of particles is just completely different, and the classical theory that you did these black hole solutions in is, unstable, suffers from the Ostrogradskian instability. So it seems to me like there's just a big disconnect there. Please respond to that.
I mean, what's happening?
Bob, did you hear my question?
Bob, are you still online?
Oh, we may have gotten disconnected.
We annihilate him, Richard.
It does not make any sense to take a classical limit of a theory where the fields are not the asymptotic states of the theory.
But you did it. That's what I'm concerned about. I didn't do this, you did it.
I think there is a problem with the connection.
Okay.
Bob, are you there?
Yes.
Okay, now it works.
Okay, so I was going to say, I was not the one who did this, you did it. And it seems to me like if I just accept everything that you and John are claiming for the ultraviolet complete theory, so I don't necessarily accept that, but suppose I accept everything about it, the classical limit of that theory can't possibly be the theory that the gravity theory, the R plus C squared plus R squared theory, in which you analyze these black hole solutions in. And so it seems to me like there's just a big disconnect there.
Yeah, it would be very similar in QCD.
But no, I don't understand why it would be very similar in QCD.
I guess it's even worse there because quark and gluons are all not in the asymptotic space, where in this theory, at least some of the fields, the graviton is in the asymptotic space.
But in QCD, we can take the classical theory, we can put it on a lattice and numerically simulate it. It seems to me like if I grant everything that you're saying about the ultraviolet complete theory, the classical limit of that, which I agree is a very interesting thing to look at for precisely the reason that you're looking at it, to try and see things about black hole solutions and everything. So I don't disagree with trying to answer those questions, but it seems to me like you're using exactly the wrong theory to analyze those questions, because the classical theory that the classical R plus C squared plus R squared theory can't possibly represent the classical limit of the theory that you claim to be using.
Well, hopefully the quantum field theory is the correct theory. So at least I have a chance of at least starting from the correct theory. So that's one step in the right direction. And as we keep telling you,
I'm sorry, I don't understand that.
The low energy theory of this theory is something that you can take a classical limit of. And as you keep saying, that's the theory where everything works great in the classical theory. So we should be happy with that aspect of this theory.
I think we have time for just one more question.
You're
Luca?
just not going to reply to my question.
May I ask a question?
Yes.
I don't know. Luca was.
No, please, Leo. Please, Leo.
No.
Okay. Bob, thank you very much for a nice talk. Very interesting. I have the following question. Can you, let's say, propose some mechanism or say something about why the ghosts cannot be created from vacuum or can be created only in pairs or be created and immediately annihilate or things like that?
As soon as it's created, it starts to propagate backward in time, which is the only odd feature of this thing. It carries positive energy. So I think all your intuition about positive energy particles still apply in this case.
If I can jump in on that, this is something Richard and I have discussed. Single ghost particle production is kinematically forbidden unless you have momenta that are up on the scale of the ghost mass. So if the ghost is heavy, you won't get it until very high energies. That is, however, there are pair production diagrams that are kinematically allowed at lower momenta. So basically along the same lines as what Bob's saying.
Oh, okay. I think it's time now to move to the next talk, and maybe to postpone the more questions in the discussion session at the end. The last talk of today